Hey and welcome back. Last video was just about the basics. This is why today we need a little bit more time. After watching this video, you will hopefully have a better understanding of and some nice tips for photogrammetry. Let's start with the object we want to scan today. I decided for this little stool. In case you watched the last video, you might notice that this object is way more complex in its texture and form, because there are two main problems we have to solve. The first problem are these shiny metal rings, because metal is absolutely horrible to scan if it is not rusty. But in this case, it has pretty good texture along all rings, so we have a good chance that the software can use this for alignment. The second problem is the fur on top of the stool. We have to make sure it is not moving during capturing, because it could give us problems with alignment. Also, the fur is pretty red, and with polarization it will be even more saturated, so we have to look out for that. To solve our problem with the reflections on the metal rings, we need to talk about polarization. Polarization is a technique used in photogrammetry to remove specular reflections from objects. To achieve this effect, two polarization filters are needed. One in front of our light source and one in front of our camera lens. When we now rotate the filter on our camera, we will see that the light passing through the filter increases and decreases depending on its orientation. This is called cross and parallel polarization. To visualize this, you can think about many lines parallel to each other. So each filter is a field of parallel lines. If we now overlay them, the light is parallel polarized. But if we rotate one of them 90 degrees and then overlay them, it looks like a grid or many crosses. So now the light is cross polarized. But this only the case if all light sources contributing to our image have this polarization. That is why you need a strong flash to outperform other light sources like the sun if you are capturing outside. One side effect of cross polarization is that all colors look more saturated. That is why in the beginning we want to take 3 photos of a color chart. One image with cross polarization, one with parallel polarization, and in the best case one without any filters as reference. Through the color chart we then can later calibrate the colors for our images. When preparing our setup, we need to make sure that our images are not too bright nor too dark. Even though this seems obvious, I say this because we use polarization, which essentially means we filter out a portion of our light. So our cross-polarized images are darker than our parallel polarized ones. So when capturing our images of the color chart, we need to find the right flash intensity depending on our camera settings. By the way, let's have a quick look at our camera settings. Because this time I will use my Sony a7R5 for capturing instead of my old Sony a350 from last video. One important part we have to consider when doing our preparation is where to place our camera and which settings to choose. Let's start with our focal length. And again, this is really up to you, but staying above 30mm is always a good choice, because then our reconstruction software later has it easier to correct the lens distortion. One thing to consider with your focal length is your depth of field. While you should use an aperture around f8 up to f16, you can also increase your depth of field by decreasing your focal length or moving your camera further away, both increasing your depth of field. Be careful with too high apertures of above f16, because even though you get a higher depth of field, you trade your detail sharpness for overall sharpness. We already talked about ISO in the last video, and the main reason for keeping it low under around 600 and at best at 100 is to not introduce too much additional noise to our images. Up next is our shutter speed. I usually go with 1/160th of a second because my flash, the Godox AR400, has a flash duration between 1/350th of a second and 1/110,000th of a second. And like this, my image without the flash would be pitch black. This makes sure only the flash with the polarization contributes to the light in the image. As you might have guessed by now, I won't move around the object today. Instead, I will use my custom turntable to turn the object. If you don't have a turntable, don't worry, you can still follow along without a problem. At this point, I want to throw in a question that is asked quite a lot from beginners in the photogrammetry community. How many images do I need to capture? If you watched my video about how the math behind photogrammetry works, you know there is a process called MVS or multi-view stereo. This process creates the depth maps for each camera view by comparing multiple views to each other, like we do with our eyes to gauge depth. So technically, this process needs 2 images from every surface to calculate good depth maps. In addition, 1 image pointed straight at the surface gives you perfect textures. So around 3 images per surface and additional in-between images for hard edges and angles. Obviously, you can't divide all objects into perfect surfaces and then calculate where and how many photos you need to take. So what you instead should focus on is if you have covered all areas of the object with your photos. If that is the case, you are probably good to go. Something that can help you decide if you have captured enough is looking at the overlap between photos. For example, in the alignment step, the software tries to find points or features that are in as many images as possible. For this, an overlap of around 80% should be the goal. These are then used to find the camera position in 3D space. But what does overlap mean? Well, it's pretty simple. If you have 2 images of an object and you can find points that are in both images, you have overlap. So it isn't about the percentile of the object being in the image, it is about how much information from the last image is in the next one. This is very important and can mess up a lot of your scans if you don't think about it during capturing. Okay, so now that we have talked about all our settings and how we need to prepare, let's take our photos. Because again, I use my turntable, I just tell it how many images I want to capture and how fast it should go, and voila, it captures my first row, starting with the parallel polarized images. Then I do the same row again, but this time with cross polarization. After that row is finished, I go a little higher with my camera instead of moving the object. That is because again, the shape and furry top could mess up our scan if they move too much. Now I just repeat this, always maintaining enough overlap when changing heights until we think we have enough photos of this side. And now I do something odd. I move the object to capture another side. Oh my god, but didn't I say we shouldn't do this because of the fur? Yes, I did. But I will turn our object upside down, being very careful to not move any of the fur on the sides, because we already captured the top and won't see it again. It is fine if the fur there moves. And after turning it upside down, we just repeat capturing our cross parallel polarization for different heights, maintaining our overlap. And that's it. We are done with capturing our object. It is time to move our data to our PC and into our image editing software. In my case, that is Lightroom. Haha, wait. We still need to create our color profile from our color chart images that we took in the beginning. For this, you need a DNG converter. Adobe has one. And a DNG profile editor. Adobe has one of these too. So now we just convert the images of the color chart into DNGs with the Adobe DNG converter. Then we take our cross-polarized image into the profile editor. Here we quickly choose the tone curve tab and the linear tone curve. Next we switch into the chart tab. Here we need to put these little color circles on the corresponding colors on our color chart and click on Create Color Table. And that's it. Now we export that profile and do that again with our parallel polarized image. So this should give us 2 profiles. In Lightroom, we import the cross and parallel polarized images of the color chart. To import the color profile we just created, we click on File, Import Develop Profile and Presets, and choose our profiles. Now we click on one image and choose Develop. Under Profile, click Browse and scroll to the bottom. Here you should see your new profiles. So select the right one by double-clicking on it. Do the same thing for your other image. Up next, we need to calculate or kind of approximate the exposure difference between our cross and parallel polarized images. I say calculate or approximate because we have at least two options. The first one is going into Photoshop and somewhat guess what the exposure difference is. The second option is using a small Python program that I uploaded on GitHub for this video. This option is more for the people who are already somewhat familiar with programming, because you need to know how to set up Python and install the needed libraries. But if you know how to do that, then you can just run the program, choose your raw image files, and the program calculates a good enough exposure difference value. And for everyone else, let's have a look at how we can do that in Photoshop. First, we need to export both polarized images from Lightroom. So select them in our library and then click on Export at the bottom left side. Under File Settings, we want to change our image format to TIFF and our color space to Adobe RGB 1998. Also, make sure your bit depth is set to 16 bits per component. Then export and save. Now we want a project in Photoshop where we import both images. To achieve this, first drag and drop one of the images into Photoshop. If a pop-up appears, choose the first option and click OK. Now, drag and drop the other image into Photoshop and press Enter. If there is a lock on one of your layers at the right, click on it to remove it. Next, click on Image in the top menu bar. Go to Mode and set the bit depth to 32 bits per channel. Continue by making sure that the cross-polarized image is at the top of your layers. Also, if there is a small symbol in the corner of one of your images in the layers, right-click on that image and click on Rasterize Layer. With the bottom layer selected, add an exposure layer and set the layer mode of the top layer to Subtract. We can now change our exposure in the exposure layer to find the exposure difference between our images. To achieve better results and make this process easier, you can put an object that has no specular reflections next to your color chart to see how much light got cancelled out due to the cross-polarization. In our case, we didn't do that, so we just eyeball it on our color chart patches. In my case, I think around -1.3 is good, so if you found the right value for you, write it down or just remember it. And you can close Photoshop without saving. We also don't need the TIFF files anymore. Going back into Lightroom, we can remove our two color chart images and then import our actual images. Let's choose our first cross-polarized image. Give it our cross profile and adjust our exposure as needed. For our parallel polarized image, we subtract the exposure value we remembered from Photoshop. So if our cross-polarized image has an exposure of +1.75 and our value from Photoshop was -1.3, then the exposure for our parallel polarized image should now be +0.45. Also apply the parallel polarized profile. In the last video, we already talked about what settings you could change to improve your photos. Our goal is to have the least amount of shadows, close to no reflections, good structure and lighting, while maintaining low noise. If your noise initially was already high because you needed to compensate a dark environment with a high ISO value, then you can use some noise reduction. But bear in mind that noise in your image is also detail, so don't crank the noise reduction too high up. And if you remove the lens distortion, I will hunt you in your dreams. Okay, so if we chose the settings for one image, we can copy these to all our images. By selecting the image we want the settings to be copied from first, and then selecting all the images we want the settings to be copied to. Clicking on Sync Settings at the bottom right in our library and choose which settings you want to copy. When all our images have their settings and we check that the exposure is nearly the same in all shots, then we can go on to exporting. Here, you can choose which file format you prefer, but going with JPEG at 100% quality is totally fine for our mesh. If you want to use different images for texturing, you can do so by exporting the images again in a different format like TIFF with 16-bit colors into a folder named _texture. I will proceed with only the JPEG files for meshing and texturing just to keep the computing times low. Because we captured two sides, and I want to explain how you can use masking to put both sides together, let's have a quick look at it. First, we want to import all images from one side in a new reality capture project. From here on, everything is pretty simple. Group the images, align the images, make a preview on normal detail mesh, remove all unwanted geometry, export depth and mask, but we only want the masks. We want these masks to be exported in a new folder right next to our _geometry folder. This one we name _mask. The mask usually get a suffix, so we quickly remove that from our images. Another option is to keep all images and masks in one folder and just naming the files point geometry and point mask. In both cases, this procedure needs to be done for all sides. And then again, we go inside Reality Capture and import all our images and again group them. Now let's have a look at our alignment settings and what they do. Max feature per MPX does exactly what it says. It defines the maximum number of feature points the detector is allowed to find in 1 megapixel of your image. Max features per image is again pretty self-explanatory. It defines the absolute limit to features per image. Image overlap tells the software how much image space is covered with the same part of the object in neighboring images. More overlap makes it easier for the software to calculate camera poses. Image downscale factor reduces the images before feature detection by the given value. Max feature reprojection error is the internal position level used during alignment. This value should not go above 3 pixels and the lower the better. For this video, and for most cases you don't have to think about the camera prior settings, control point prior settings and draft mode. The next interesting settings are the advanced ones. I will just go through the important ones here. Force component rematch will, when set to true, realign images among each other in order to find better connections. Pre-selector features are the number of features that will be used in alignment from the ones that got detected. This should be around 1/4 to 1/2 of the detected features. The detector sensitivity tells the feature detection algorithm how it defines which points are usable as features. Ultra, for example, will detect more features in weak texture places, but it is likely to detect noise as features. Low is the exact opposite and can lead to throwing away feature points that could have been used for alignment. Distortion model defines which distortion model you want to use. I put a link in the description where you can read about those. By the way, is this the point where your lens distortion is important? Okay, so for now I'll leave the settings as they are and click on Align Images. And now we just wait for the software to be done. As soon as the alignment is done, we get some components. If one big component with close to all images is there, we did good and can continue. If that is not the case, we need to change some settings and try again. If we can't get them to align, whatever we try, then you can use control points. But we don't need them right now. If you need them, have a look at the video in the description about the usage of control points. Now, if everything is aligned, we can try to lower our reprojection error around 1 pixel and align again just to make sure our position is on a good level. After this, we can hop to the Mesh Model tab. The settings for meshing are actually not that impactful, but if you are interested, there is a link in the description. To make sure only our model gets reconstructed, we can click on Set Reconstruction Region and change the bounds in which the mesh gets calculated. In the Scene 3D Tools tab, we also have this option, but additionally, we can change our ground plane. This allows us to rotate and position our model in the viewport. If you just want a quick preview of your model, you can click on Preview, which just creates a model through the sparse point cloud. This model is obviously not really detailed, but it can show you if there are major errors already. If the model looks fine in the preview, then we can decide to create the normal or high detail model. The only difference is that the normal detail uses half the resolution of your images, resulting in faster processing times, and the high detail uses the full resolution. I always go with high detail to get the highest quality possible, but be aware that this can increase your meshing time significantly. To give a quick example, I just did a scan for a museum, from which I had 1198 images of a furnace. Every image having 60 megapixels, the high detail model took 21 hours to render on my AMD Ryzen 5900X and RTX 2080 Ti. To compare the speed, I then set the normal detail to 1/3 of the original size, so around 20 megapixels per image. This only took 1 hour and 21 minutes for the meshing. So scaling down your images or cropping them can give you a reasonable speed increase. At this point, before meshing, we also want to decide if we want to use all our images for meshing or just our cross or parallel polarized ones. In most cases, just the cross polarized ones are our goal. To do this, we can go through all images and deactivate the ones we don't want to use for meshing with Ctrl R. In my case, I actually used both. When our meshing is done, we have a pretty dense and high poly model. That can be a pretty huge problem, because there aren't many software that can handle such a high triangle count. So let's start with simplifying it down to a size where we don't lose the important details, but have a more manageable triangle count. Here, dependent on the software you have access to, you might need to sacrifice some detail, so you can work with the model later on. If you only want to use reality capture and no external software, then you are limited to some easy functionality. Reality capture offers the ability to remove floating and disconnect the pieces. You can also smooth your model or filter out geometry that you selected. All in all, just some easy to use tools. If you look for a free 3D software, you probably think about Blender. Blender isn't really good at handling huge poly or triangle counts, but up to 2 or maybe 3 million you might be able to work your way through it. The advantage of using Blender is the great range of tools and features. From modeling and retopology to sculpting and rendering, you can do it pretty much all in Blender. When it comes to high poly counts and dense meshes, the go-to software for post-processing your model is probably ZBrush. Even though the UI is scary in the beginning and everything is unintuitive, ZBrush has a bunch of features pretty much all able to handle huge poly counts. But you need to pay for it. They have different payment plans like every other software, with the standard monthly subscription which would cost me €41.65. So if you know which software you want to use, you can export your model, and if you haven't already, pay for the inputs used for processing the model. Even though I think you have to pay for all images, excluding the layers for texturing or masking, that are in the project, even though they were not used for generating the mesh. So you might want to remove the images from your project if they were not used for processing. When exporting, you have some options for different file formats. But I would always go with OBJ if you don't use any software from Autodesk, for which FBX might be a reasonable option. Now, you can refine the high poly version if needed in your external 3D program. But make sure to not mess with any of its coordinate properties like scale, rotation and position. If you are done with that, we can re-import the model into Reality Capture and again go to our Mesh Modeling tab. But this time we are interested in texturing our model. But before the texturing can start, let's have a look at the settings. The first settings are the default unwrap parameters. These are only important if you haven't already unwrapped your model. If you click on the unwrap button in the top bar next to texture, you also have some more options for direct unwrapping in Reality Capture. But let's stay in our texturing settings. Most things here should be self-explanatory. If you use JPEG images for texturing, you have the option to change your texturing style to photo consistency based, which is slower than visibility based but can give you better results. The texturing image layer setting is where you can set your texture layer as your source to use your TIFF files if you chose to use them. Because we have only one layer, our geometry layer, but we want two different textures, one time cross-polarized and one time parallel polarized. To do this, we again go over our images, deactivating half that are parallel polarized, then we texture our model with only cross-polarized ones. After that, we invert that process and texture our model only with the parallel polarized images. Through this process, we get two textures. One made out of our cross-polarized images and one made with our parallel polarized ones. If we now want a lower resolution version of our mesh, we can either create one ourselves through retopology or we just decimate our mesh again in Reality Capture. And instead of texturing this model again, we can use the Texture Reprojection tool in our Scene 3D Tools tab. Here we set our high poly version of the mesh as source model and our low poly version as result model. We want to project both texture layers, so we need to do this process 2 times, and also we enable normal projection. And we click on Reproject to start the process. If your model has no UV unwrapping yet, you will be asked if you want to create one with the current settings, and that should be okay. Now, your lower resolution mesh should have 3 textures: the cross-polarized, the parallel polarized and the normal texture. But what do we do with the cross and parallel polarized textures? Well, let's export them the same way we exported our mesh earlier, but this time we want to just export our textures. Next, import them into Photoshop in the same project. Let's set the bit depth to 32 bits and make sure the layer with the cross-polarized image is on top of the parallel polarized one. Set the layer mode of the top layer to subtract and the magic happened. What you should now have is a specular albedo texture. But we ignore the color, so let's merge them into one layer and then convert the image to grayscale. Last, set it back to 16-bit and export your new specular texture. Now, you can use your cross-polarized texture as diffuse texture. You have a specular texture and a normal texture. And with some artistic skills, you can create a pretty good gloss texture from the specular texture and some reference images. Now, you are ready to use your model for your game or next render. I hope this video helped you get a better understanding of the workflow and gets you closer to your goal. I know this video created a bit of a gap to the last video because it took a bit longer to create, but I think it was worth the time. So see you in the next one.